Right, so in the last video I referred to molecular modeling in terms of the steps that are taken, and there are 4 steps that are really important with respect to molecular modeling. One is you define what problem you need to address. Then, once you've defined the problem, you build the model. Once you have the model, then you can do a calculation, and there are many things that can be calculated. And finally, you analyze results. One problem that we have when building a model is that if we build a physical model, you tend to run out of pieces to build that model. So I might have run out of toothpicks for a complicated molecule with bonds, or you might remember from first year when you needed to build a really large molecule, you didn't have enough connectors or enough piping to create that molecule. So what we tend to do is not create physical models, but we tend to use software to do that, because software never runs out of connectors, it never runs out of bonds. So we are able to construct models, so containing quite many atoms, for example, and very different types of chemical functionality. These can all be done with software. We can not restrict ourselves to carbon atoms, but we can have oxygen atoms, you can have nitrogen atoms, you can have anything that's on the periodic table, and of course we can add hydrogen atoms, and we can clean the geometry to make it look, make the bonds have a reasonable length. This is very useful, and we can construct models in this way, but I want to take a step back, because when you construct a model in this way, the software is really helping you to place the atoms, and how you're placing the atoms is in 3D space, which means that every single atom is going to have an X, Y, and Z coordinate. So within Discovery Studio, for example, I can select any atom like the carbonyl oxygen, and I can have a look at its attributes, and you will find within its attributes it has a position in 3D space, an X coordinate of -0.81, a Y coordinate of 0.41, and a Z coordinate of -0.45. So every atom has Cartesian coordinates, and they are placed in 3D space. So this means that you don't need software such as Discovery Studio Visualizer to build a model. You can simply build a model from X, Y, and Z coordinates. So for example, if I wanted to build a model of water, all I would need to know is some X, Y, and Z coordinates. And to make it simple, I can place the water in the XY plane, which means that all the Z coordinates will be 0. So what would be nice is if I could place the oxygen atom maybe at the origin, so at 0.00, for example. Then of course I've got to place a hydrogen atom appropriately far from it, and it should be, I can be a little bit more accurate than just 1 angstrom. I can make it maybe 0.96 angstroms apart, and then finally I need a Z coordinate, and to make it match I'm going to do -0.9 and -0.32. Okay, so this is a perfectly valid way of building a water molecule. But how do we visualize such a water molecule? Well, we're going to have to then plot on graph paper where all of these atoms are, if we really wish to visualize it. We could actually carry on with the calculation. There's plenty of calculations that we can do here. We could use, knowing their positions, we can use Pythagoras to calculate their distances. So we don't have to visualize the water molecule to do, but it's often useful, and one of the important reasons for modeling is to be able to visualize what we do. So let's see if we can visualize it. So the first atom that we'll try and place on graph paper is oxygen, and that oxygen will be placed at the origin at 0, 0. So here are the coordinates over here, and I've found the origin at 0, 0, xy. I'm ignoring z for now, and so the oxygen atom is going to be placed at 0, 0. So I'm going to delete those and just place the oxygen at the position it should be. Then let's have a look at the next hydrogen at x is 0.0 and y is 0.96. That's placing it up at the top there. That's where the hydrogen will be, and so I'm going to then place my hydrogen there. And finally, the last hydrogen is at minus 0.9, which is down here, and minus 0.32, it's about there. So there we are, that's correct, and I can place the hydrogen atom there. And we have plotted the water molecule to visualize. However, you might say we have a problem with this water molecule in that there are no bonds. Well, actually there are bonds, because we know very well what a hydrogen bonded to any other atom looks like. And a hydrogen bonded to any other atom is at a distance of about 1 angstrom and often less. And the distance between that hydrogen and that oxygen is less than an angstrom, so it clearly must be bonded. Have a look at this hydrogen to this hydrogen. That distance is about 1.8 angstroms. That's too far for hydrogen to be bonded, so we know that that hydrogen is not bonded to that other hydrogen. And because this hydrogen is also close to the oxygen, that must also be bonded. So simply from the distances between atoms, I know where the bonds are, and I do not need to record it when I'm recording the molecule in Cartesian format. Of course, you don't really need to know bond lengths. You can use your chemical intuition as to where you draw your bonds. You have a central oxygen atom, you've got hydrogen atoms around it, you know where to draw those bonds. So it's very easy then to draw that water molecule and visualize it. But all the information needed is contained in the Cartesian coordinates. Right, but what about this file? This is a file that I've opened that contains information about a water molecule, but you'll notice that it does not have the same values that we had in the previous case. And if you look carefully, you can see an oxygen and 3 values next to it, a hydrogen again with 3 values. And we can be clear in almost all molecule formats, the 3 numbers are most certainly an x coordinate, a y coordinate, and a z coordinate for each of those atoms that are in the model. So we can have a look at this. We can see if we can visualize this water molecule. And so just to simplify it, I'm rounding off some of the Cartesian coordinates to make it easier to plot. And then we can plot the oxygen atom is at minus 0.74, minus 0.55. I can plot a hydrogen atom, and I can plot the other hydrogen atom. And of course, chemical sense says where the bonds are going to be in this case. And so we can place the bonds in, and we see we have another water molecule. But interestingly, a water molecule that is in a very different orientation and in a very different position to our original water molecule. So if I were to overlay those 2 water molecules, you can see that they are both water molecules, but they're in very different positions and very different orientations, very different rotations. Now, of course, if water is interacting with something else, then we know that the orientation and position of the water is important. But if we were trying to model water on its own, then the position of a water in 3D space and its orientation is not important. I'm not saying the position of atoms relative to each other, but the position of a water molecule itself. Whether it's at the origin or not at the origin will not affect the water molecule if it's on its own. What I'm trying to say is that Cartesian coordinates, when we use those to describe molecules, if we're trying to model the molecule on its own, those Cartesian coordinates contain too much information. They contain translational and rotational information, which may lengthen calculations in certain cases. So it would be interesting to see if we can find a different way to represent molecules with less information that's perhaps more efficient when we come to do calculations.